time for us to do some problems involving arc length, which means once again we go into battle against the square root. Well, hopefully we will come out victorious on the other side. Of course, the way we win is we do more problems. The more we do, the more we learn to say, hey, this is not so scary. It's possible. A lot of it just comes down to algebra and learning to simplify, and of course, practice, practice, practice. So make sure you're doing as much as you can on your own. And if you're following along with this video, make use of the pause button. Pause and say, okay, what would I do? Where would I go? And go there, and let's see. And of course, if you need help, I'm right there ready to act as a backup guide. Well, let's get going on our journey. So our very first problem. Find the length. Aha, length. Okay, that's how we know it's an arc length problem. It gave it away. The curve y equals natural log of x minus 1/8 x squared for 1 less than or equal to x less than or equal to 3. And simplify your answer. Now you often see things like this here. You kind of, after you do this for a while, you're like, yeah, okay, I can see a pattern emerging here. So what's the rule? Well, the length is you're adding up, which is another fancy way of saying you're integrating from the start to the stop. And then there's the expression, square root of 1 plus the derivative squared and dx. Now, there you go. That's what you're looking for. All right. So, okay. By the way, you might be thinking, how do I remember that? Well, you do, right? You memorize it. Another way to think about it, you can sort of think about what's happening if you were to zoom in. So, what's happening? Well, if we have our curve, so there's our curve, and we were zoomed in, so it looks kind of flat. And now we say, hey, let's imagine we look at our curve. Well, we can think of our straight line. There's a little piece, which is our change in x. And then, well, how much do we go up? Well, the answer is, we can say this is really f prime of x, change in x. And then we say, okay, Pythagorean theorem. If it's dx here and f prime of x dx there, then the missing side is the square root of 1 plus f prime of x squared dx, because dx is common to both. So really, this is like Pythagorean theorem. Not surprising. Pythagorean theorem is really all about length. So if you're stuck remembering, think of the picture. Think Pythagorean theorem, and there you go. All right. Well, for us, we see our start and stop, 1 to 3. The square root of 1 plus, now take the derivative. Derivative of natural log, 1 over x. Derivative of minus 1/8 x squared, well, that's minus 2/8 x, or 1/4 x. And don't forget the square, squared dx. So 1 to 3, 1 squared out. So 1 over x squared, okay? The first term squared. Then your cross term, 2ab. The x's cancel. And then, what do you really have? Minus a half. And plus, last term, 1/16 x squared. Now, if you've lived a good, clean algebra life, which of course we'd have. Of course we have. And we always strive to do that. Then something nice should happen. And here we see, hey, something nice is happening. This 1 combines with that minus a half. In fact, in a very nice way. So that the minus a half now becomes plus a half. So it's sort of a small change. So 1 to 3 square root of 1 over x squared plus a half plus 1/16 x squared dx. And now, at this point, we start saying, this piece that we are now working with is awfully close to that piece. The only difference is the plus versus the minus. And we also know that this piece is a perfect square. So we start to be suspicious. Perhaps we have another perfect square. Well, we deserve to be suspicious, because oftentimes when we're dealing with length problems, if we actually have a chance to make progress, oftentimes a perfect square is lurking somewhere. And so we say, hey, this would be the same thing as if we had started with this expression, but with a plus. So that's what we do. Say, well, look, that's really 1 to 3, the square root of 1 over x plus 1/4 x quantity squared. So now the square root, the square, undo each other. So we have integral 1 to 3 of 1 over x plus 1/4 x dx. Well, we're most of the way there. Now we can integrate. Integral of 1 over x is natural log of x. Integral of 1/4 x is 1/8 x squared, right? Because you'd add 1 to the exponent, divide by 2. Notice, suspiciously similar to what you have there. And we're not done. We're really close. Now we need to evaluate 1 up to 3. Well, what does that become? Well, natural log of 3 plus 9/8, all right, subtract natural log of 1, and then plus 1/8. And here we say, hey, natural log of 1, we know what that is. Natural log of 1 is 0. And here we have 9/8 subtract an eighth. That's beautiful. That's 1. And natural log of 3 is, well, it's natural log of 3. You know, that's what it is. It's already really as simple as it can be. So our final answer is 1, which comes from the 9/8 subtract 1/8, and then plus the natural log of 3. And there we go. There we go. Good. Good. Now, one thing we should get into the habit of doing is sort of checking, is our answer reasonable? So maybe we haven't said this explicitly enough. Let's do it right now. If we're looking for a total length, what should be true? Well, it should never be negative. If we get a length and say, hey, we've gone -7 feet, whoa, something's wrong. That's not a length, okay? So a length should be a positive thing because it's a measurement. There's no orientation. There's no positive, negative. Okay, so we're fine here, 1 plus log 3. There's another kind of reasonable check you can say. It's like, well, look, I know I'm going to start at 1. I'm going to end over here at 3 somewhere. Of course, slightly off. Well, I definitely have to move at least 2 units to go from 1 to 3. So my answer better be at least 2, right? Well, log of 3 is a little bit bigger than 1, so that's good. It matches with our idea that we better have moved at least 2. And of course, on the other hand, if we got an answer like 1,000,000, we'd say, whoa, wait a second. That doesn't seem right. It shouldn't be so big. So one of the nice things about applications is there is sort of a built-in, does it seem to be reasonable based on the intuition? And if it is, then it's like, okay, good. We're fine. We're fine. So, and there we go. All right. Well, on to some more problems, some good fun problems. So, our next one. Find the length of y equals 1/2 e to the x plus e to the negative x. Okay, now we could do this problem exactly like the one we just did. In fact, if you go through it, you'll see a lot of the same things happen. We're going to have fun and do this in sort of a weird way, and by doing a little bit of, hey, do you remember? And if you don't, now's a great time to learn. So here's the fun thing. This function, 1/2 e to the x plus e to the negative x, is not just a random function. It has a name. So this function is called the cosh function. Cosh of x. And what it is it's the hyperbolic cosine. Now you might be thinking, wow, that's interesting. I've never seen the hyperbolic cosine, except you have. Now, you might say, what? How do you know what I've seen? You haven't lived with me. You haven't been where I've been. Well, let me draw you a hyperbolic cos. Okay, hyperbolic cosine, what does it look like? Well, it looks kind of like that. Now, I'm going to draw a little bit more here, and bear with me. I did take a drawing class many, many years ago, but you have to imagine that I could still draw. So I'm going to add a little bit here, and you'll start to see something familiar. And hopefully you'll see something that looks a little bit. There we go. All right. And aha! Even I think I might recognize that. That looks a little bit like a bridge because it's a bridge. So it turns out that if you have a bridge, like for example in San Francisco, they have the Golden Gate Bridge. Then what it is that cable that hangs, that hanging cable, it forms the shape. The shape is the hyperbolic cosine. So it's a really interesting curve in terms of practical applications. It shows up out there in the wild. So it's not just a fun like, ooh, this is cute. We can do these things with e to the x. Ha 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 ha. No, this actually shows up. So it's important to know it. Now, we're asked to find the length of the Cauchy curve. So you might say, well, what are some things we can say about Cauchy? Well, it turns out there's a couple of fun things. There's another function related to it called sinh. What is sinh? Well, it's very similar, except instead of plus, it's a minus. So that's sinh. Now, at this point, you're probably also thinking, why do you call them cosine and sine? Hyperbolic, cosine, hyperbolic, sine. They don't look anything like cosine and sine. Now, here's the really crazy thing. And this is true. This is true. Cosh and cosine are actually kind of the same function. But what we mean by that gets a little bit complex. We'll finish the story about how these functions are connected to each other by the time we hit the end of Calculus 2 here. So hang in there. It might be a while. It's probably a lot of sessions down the road, but we'll get there. We'll get there. So wonderful story. All right, now we'll need a couple of fun facts. And these are all very easy to prove. So what's the derivative of Cauchy? Well, it turns out it's sinh. Easy to show just from the definitions. Okay. What's the derivative of sinh? Well, it's Cauchy. So at this point, you're probably thinking, wow, it's even better than sine and cosine, because sine and cosine, you have that annoying, well, one of them you have a minus and one of them you don't. Here's something else that's really fun. It's the following fact. If you take Cauchy squared, subtract sinh squared, you get 1. So it's sort of like the cosine squared plus sine squared equals 1, except it sort of turns it a little bit. So Cauchy squared minus sinh squared gives you 1. All right, that's all we need. So that's all we need to do the problem now. So here we go. You ready? So we're asked to find the length of the Cauchy curve from 0 to log 2. So we say, well, the length formula is adding up, start to stop, square root 1 plus the derivative squared. So far, so good. Now, our function is Cauchy, so what's the derivative of Cauchy? Well, the derivative of Cauchy is sinh. Okay, so that's the square root of 1 plus sinh squared x. All right, now, can you do anything with 1 plus sinh squared? Can you? Look, if you move this to the other side, 1 plus sinh squared is Cauchy. So this becomes integral a to b of, I should say Cauchy squared, square root of Cauchy squared. All right, whoop, a to b, we know our bounds, 0 and log 2. Let's update our bounds. 0, log 2. 0, log 2. There we go. Square root of cosh squared is cosh. That's good news for us. So that means all we have to do is take the integral of the cosh. Well, so we're asking ourselves the question, is there some function that when we take the derivative of it gives us cosh? Well, we do know a function. The derivative of sinh gives us cosh. And therefore, the antiderivative of cosh is sinh x. 0 to log 2. And now we're basically done. We just have to plug everything in. So what do we have? Well, we have to plug in log 2. So if we plug log 2 into sinh, we'll actually go back to our definition. So that's 1/2 e to the log 2 minus e to the minus log 2. And then when you plug in 0, well, e to the 0 is 1. E to the minus 0 is 1. 1 minus 1 is 0, so you get 0. Okay, e to the log 2 is 2. So we have 1/2 times 2 minus, now this e to the minus log 2. Now be careful, this is not, the minus here does not cancel with that minus there. No. What does it do? Well, what you can do is you can say, yeah, we can have the following. You can think of this minus in front as going in, so it's 2 to the minus 1, also known as a half. So this becomes 2 minus a half. So that's what this happens to this e to the minus log 2. 2 minus a half, that would be 3/2, also known as 1.5, times another half. So that would give us a grand total of 3/4. And therefore, that's the distance, 3/4. That's how far the cosh curve, total length of the cosh curve, from 0 up to log of 2. Now, of course, if you didn't know about cosh and sinh, you can still do the problem in the exact same way as you did the previous problem to this one. But this is kind of fun. See, the more you know, it's like, hey, you can pick up little pieces, and it's really fun to play with. All right, well, let's do another problem. So here we go. You've recently been hired to lay cable. Now the job is very particular and requires that the cable be laid along a curve of the form y equals 2/3 x to the 3/2. Oh, that is very particular. Where we start at the origin and then move along the curve for increasing x, where both x and y represent distance in meters. Given that you have 42 meters of cable, determine the point, the coordinate x, y, where the other end of the cable will be. So what's happened here? Well, we have our curve, 2/3 x to the 3/2 power. I don't know exactly what that looks like, but well, let's just say it's doing something more or less like this. All right, so here's our curve, y equals 2/3 x to the 3/2. And now we're laying cable along the curve. So we're going to start putting cable down. Now, how far do we go? Well, the answer is we start here and we keep going up until we have a total length of 42 meters. In other words, we go until we run out. So the problem here is not that we need to find the length. We actually have the length given to us. So the question is, well, given that we know how much length there is, where did you stop? Turn the question around, I see. Okay, well, this could be interesting. So let's start thinking about what we have. We know a couple of things. We know our basic length formula. So length is adding up, or if you like, integrating from the start to the stop, the square root of 1 plus, I'll say the derivative, y prime squared dx. Well, I know what the length is. It's 42. So that tells us 42 is integral. Well, I know where we start. We start at 0, because it tells us we start at the origin. That means 0. And we go till we stop. Okay, that's what we don't know. We don't know where we stop. So I can't put in a value for b, because that's what we're trying to find. If we already knew what b was, there wouldn't be any problem for us to do. Okay, the square root of 1 plus, now we take our derivative. Well, derivative here, 3/2 comes down, 2/3 times 3/2, 1, and then it's 1/2 power, right? Because you subtract 1. X to the 1/2, and then squared, dx. Well, that's integral 0 to b of, well, what's x to 1/2 squared? It's x. So this becomes x plus 1 to the 1/2 power. Okay, we can make progress. This is actually a very easy integral. The square root really poses no problems at all. And so we say, all right, well, let's integrate. And when we integrate, well, what would we get? Well, we'd have add 1, so that'd be to the 3/2 power, and then we multiply 2/3 in front. Evaluate that from 0 up to b. Okay, so what is that? Well, all right, that's 2/3 times b plus 1 to the 3/2, because that's what we get when we plug in b. Subtract, now plug in 0. 1 to the 3/2, well, that's just 1. All right, now what do we see? Well, we see 42 is equal to this expression. And the last part is to say, we need to solve for b. That's what we're after. So we start doing our algebra, gently coaxing it, getting it loose, and say, okay, come on, algebra, work with us, work with us. Well, let's think about things we can do. Let's get rid of the 2/3. How do we do that? Well, multiply across. So I'm going to multiply by 3/2. 42 times 3/2, well, you can take the half, so 42 over 2 is 21, times by 3 gives us 63. Good. So we now have 63 equals b plus 1 to the 3/2 minus 1. Well, let's move the minus 1 over. 64 equals b plus 1 to the 3/2. Well, let's get rid of the 3/2 power. So the way to get rid of the 3/2 power is to take both sides to the 2/3 power. So we have 64 to the 2/3 is equal to b plus 1. Of course, now we start to wonder, well, what is 64 squared? Well, what is 64 squared? 4,096, right? Well, of course, that's not what we would do. What we'd really do is say, look, what's the cubed root of 64? Does it have a nice cubed root? Well, it turns out cubed root of 64 is 4. 4 times 4 is 16. 16 times 4 is 64. So, if I think of this as 64 to the 1/3, and then square that, what happens? Well, 64 to the 1/3 we just said is 4. So this is really 4 squared. And 20 years ago, oh wait, no, that's something else. That's 16. So b plus 1 is 16. So finally we get to the point where b is 16. Now, is that our answer, and why not? Good, you're right, it's not our answer. But why not? Well, we have to be careful. It says, find a point. See, we need a point. Our answer has to be a point. So we have to think about what our answer, well, 16, no, it's not 16. No wonder you didn't say that was not our answer. It's 15, right? Because we have to subtract 1. Okay, 15. Is 15 our answer? No! Okay. But again, it's because it's not a point. Okay, so we're going to make it a point. So we know, what is b? Well, b is where we stopped for x. So it's the x coordinate. So our final answer will have 15 for the x coordinate. What about the y coordinate? Well, we plug it into the function. So 2/3 times 15 to the 3/2 power. And that's where the end of the cable will be. All right, good. All right, we made it. Well, interesting problems. So, let's do another problem. Woo! All right. So find the length of x equals 2/3 times 4y squared plus 1/2 to the 3/2, where y goes from 0 to 3. Now notice, we're switching to y. Does that switch our technique? Nah, no problem. Really, it's just a matter of just a different symbol. We're not caught up by symbols. The ideas don't change. That's the important thing. So what do we have? Well, our basic formula. Length is all about adding up, start to finish, of the square root of 1 plus the derivative of our function. In our case, it's a function of y, so g prime of y squared. Don't forget the square. That's really important, because if you don't have that square, things will get really hard. And you're like, why is this problem so hard? Well, because we forgot something. So we want to make sure we don't forget. And then dy. It's important to have the dy. You know, as we go through these applications, dy represents things. Let me just point this out. We should think of dy as sort of like a change in y, and y is a length. It's measuring location, so change in y, change in length. So this is really a measurement. And then this quantity, it's a value, it's a number. So it's a scaled number. So that's why we say, aha, this is when we put it all together, it's a length. And so we say, okay, we're adding up lengths. And you'll see in more and more applications, you're like, oh, okay, this dy represents that quantity, or this dy represents that type of quantity, and it all comes together. So it's not just there for show. It means something. It means something. All right, so let's go. Keep going. Into the algebra we go. So this will become the integral, start to finish, 0 to 3. 0 up to 3. The square root of 1 plus. Now, careful with our derivative, 2/3. Then we say, okay, the 3/2 comes down. So times 3/2. Ooh, that looks promising. Of 4y squared plus 1/2 to the, okay, now the power here. 3/2 subtract 1. 1/2 power. Are we done? Oh, there's something before the square. Chain rule. Okay, so now you have to multiply by the derivative of the inside, 8y. And that now squared. So this square is this whole thing, dy. Okay, progress, good. Now, we say, okay, we can clean this up. We can say the 3's, the 2's cancel, almost as if they were meant to cancel, because they were meant to cancel. Oftentimes, these problems are very delicate in that they've been set up so that some beautiful algebra will happen. So let's see what beautiful algebra happens here. 0 to 3, square root of 1 plus, now we have the 1/2 squared. So that'll just leave us with just to the 1. So 4y squared plus 1/2. Now square this term. 8 squared, 64. And y squared is, well, it's y squared. Okay. Now we expand. So this would be integral 0 up to 3, square root of, and 1 plus 4y squared times 64y squared is 256, because 4 times 60 is 240. 4 times 4 is 16. Put them together, 256. Y squared, y to the 4th. 1/2 times 64, 32. Y squared. Okay. And there we go. Now, right now, it doesn't look promising, but we've just started the algebra. There's more to come. So what can we do? Well, it's polynomial. We should rearrange it so we have things in sort of the right order. And when we talk about right order, we'd like to go from high degree to low degree. All right. So integral 0 up to 3, square root of 256, y to the 4th, plus 32, y squared plus 1. Now, at this point, we start saying, it would be so nice if this was a perfect square. Especially when we see sort of 3 terms being added together. So when we see things like blah, 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 it would be nice if it was like a squared and 2ab and b squared. Well, maybe it is. Maybe the algebra is working with us today. Well, let's see what would have to be true. So in order for this to be a squared plus 2ab plus b squared, well, we can see what this one would have to be. That would have to be 1 squared. Okay, that's not so surprising. Okay, how about 256? Is that a square? It is. It's actually 16 squared. So this is 16, and then y to the fourth would be y squared squared. Now, we ask ourselves the question, okay, if a is 16y squared and b is 1, what would 2ab be? Well, what would be great is if we multiplied it all together and we got, oh, it does work. Look, 32. It's 32. It works. It works. It is a perfect square. Ah, yes. That means we can continue to make progress. Ah, good. This is great. This is great. So integral 0 to 3. So this is really a squared plus 2ab plus b squared, which means it factors as a plus b squared. Now, of course, that's not so bad. We can really say, look, square root of a square. See, that helps us get rid of the square root. Ah, and isn't it nice when we don't have to deal with the square root? I'll tell you, it's a challenge, square roots. They're tough. They're tough. Okay, but now we have a very pleasant integral. So let's see where we end up. So we integrate. Okay, so this would be 16 thirds y cubed plus y. And evaluate 0 up to 3. Yes? All right. All right. Good. Well, 3 cubed, but notice it's actually not 3 cubed because what do you have? You have a 3 downstairs. So one of the 3's cancels, so it's like 3 squared, 9. 16 times 9, you're probably thinking, gross. Exactly! It is gross because 16 times 9 is 144. A dozen, which is another term for gross. So plug that in. So we get 144 when we plug in 3 there. And of course, plus 3 more. And then we subtract when we plug in 0. Well, that's just 0. Leaving us 144 plus 3 makes 147. Wow. Wow. Amazing. Amazing. What a beautiful number. And probably not the one we would have guessed when we started. But fortunately, the algebra, we were careful. We respected the algebra. The algebra worked with us. And that's a good rule. Work with the algebra, not against the algebra, with the algebra. All right. Well, more problems to do, right? Of course. There's always more problems. So let's try another one. Find the length of y equals log secant of x, where x goes from 0 to pi fourths. Oh, well, okay. Interesting. A different kind of problem. One with the trig. We really haven't done one with the trig one yet. I wonder what's going to happen. Well, one way to find out. So length, we're adding up, start to finish, our square root of 1 plus our derivative, all right, as dy dx squared, and then times our change in x. So for us, 0 to pi over 4, because start to stop, all right, square root of 1 plus, now, log secant. Do we know what the derivative of log secant is? In fact, log secant might sound familiar, like we've heard it somewhere before. And if you think back, you might say, hey, wait a second, the integral of something is log secant. You're right. Do you remember what it is? It's the integral of tangent. The integral of tangent is log secant. If you take the derivative of log secant, we'll actually do it just to remind ourselves. It's 1 over secant, but then the derivative of secant upstairs is secant tangent. And so what happens is the secants cancel, and you just end up with tangent. All right, don't forget the square. So, now we look at this and say, well, we have the square root of 1 plus tangent squared. All right. We like to get rid of the square root. So we ask ourselves the question, well, can I rewrite 1 plus tangent squared in a nice way? In some way that I don't have a plus, just like a single term. And we start digging around in our trig identities, but we don't have to dig very far because there's a very familiar trig identity which is related, which says that 1 plus tangent squared of x is equal to secant squared of x. Aha! Well, that's very convenient. Wow, almost too convenient. But we will take our win. So this becomes 0 to pi fourths square root of secant squared of x dx. Okay, well, we can get rid of the square root now. You see, we're able to use a trig identity to remove a plus. And this is going to become an important theme in an eventual later session. But trig identities can be useful for collapsing things down. And of course, the problem with trig identities is not that they're not powerful, it's just that there's so many, and they're too powerful. So you have to sort of figure out which one is the right one to use. So we're down to the integral of secant. Okay, can we integrate secant? Do we know what the antiderivative of secant is? And we're supposed to. Okay, that's one of our basic antiderivatives. It's kind of the weird one. It's like the one that makes you go like, what? That doesn't seem obvious at all. It is the natural log of, do you remember? Secant plus tangent. Yeah, it's a weird one. Weird one. It's one of those ones that you kind of like almost have to remember. Some 0 to pi over 4. Okay. So, plug in pi over 4. Natural log secant pi over 4. Whoops. Plus. That's a really big plus sign. Okay. All right. I can't make it look like a really big plus sign. All right. Try it again. Natural log secant pi over 4 plus tangent of pi over 4. Subtract natural log secant 0 plus tangent 0. Now, if we think about what's happening here, tangent of 0 is 0. So tangent of 0 is 0, which means that this term is gone. Secant of 0 is 1. Log of 1 is 0, so this whole term is gone. Tangent of pi over 4, well, that we should know. It's a very common term. We see it a lot. So that's 1, which gets us to secant of pi over 4. Do you remember what that one is? Well, if you can't remember, think of it as 1 over cosine pi over 4. Cosine pi over 4 oftentimes is thought of as root 2 over 2. And if you flip it over, what you end up with is root 2. And therefore, our answer becomes natural log of the square root of 2 plus 1. Wow. What an answer. What an answer. And it's just one of those things that you wouldn't expect. It just doesn't seem like it would be true. But it is. And we can find it. Isn't it great? What a time. What a time to be doing math. It's fantastic. Good stuff. Good stuff. Well, our final problem. Our end. We've reached the end. Well, for now. There will always be more problems. So, here we go. For x from 1 to 5, find the length of the curve. Whoa. Good thing. We have plenty of time, right? Because we might be here a while. Now, here's the thing, is it looks intimidating. Because we were thinking like, I have to integrate that. Oh, my goodness. But remember, there's a process here, and there's going to be some stuff happening in between. So things that look bad at the start oftentimes have to be bad so that when you reach a certain point, things work out nicely, and then it becomes great. If things look too nice at the beginning and you manipulate, all of a sudden you're like, and things get really unpleasant. So don't let scary looking stuff stop you. Say, look, let's proceed with caution and let's see where we get to. So we begin with our bit of caution. All right, Well, we know our formulas. We know its length because it says length. It's a good clue. So length, we're going to add up, or if you like, integrate, a up to b square root of 1 plus our y prime squared dx. I suspect that the majority of this problem is going to be trying to figure out what is y prime. So let's put this aside for the time being. We'll come back to it, and let's figure this out. So y prime. All right, so there's a half. Well, there's a half times. Come to the first piece. All right, product rule. Derivative of x is 1, then times the square root of x squared minus 1. Okay, so far so good. Plus x. Now we have to take the derivative of the square root of x squared minus 1. Now, for convenience, let's just remind ourselves that the square root of x squared minus 1 is the same thing as saying x squared minus 1 to the half. So, when we take the derivative, the half comes down. X squared minus 1 to the minus a half. All right, the half comes down, inside, subtract from the power. Don't forget the chain rule. Times the derivative of the inside, so times 2x. Done. Good. Minus. Natural log says 1 over the inside, x plus square root of x squared minus 1, times the derivative of the inside, which is 1 plus, and then the derivative of square root of x squared minus 1 again. Well, it's the same thing as what we had over here. 1 half x squared minus 1 to the minus 1 half times 2x. Okay, there. You got y prime. Now, at this point, you're probably thinking, good, we just plug it into there, right? Whoa, whoa, whoa. You got to do something with y prime, so you want to simplify. If you were just saying find y prime and say, okay, great, stop here. But we want to do things with y prime. So we're like, let's make it look as nice as we can because we love ourselves and we want to take care of ourselves. So we start saying, well, let's clean things up. What do we have? Well, we have a 1 half. We get a square root of x squared minus 1. All right. Now here, what do you see? Well, there's a half and a 2. So, okay, that's going to simplify. That's good. In fact, the same thing will happen later, so we'll go ahead and do that now. And so what's this? Well, you have x times x, which gives us x squared. And then there's a square root of x squared minus 1. Okay, that's good. Progress. Now, over here, well, 1 over x plus square root of x squared minus 1. And then upstairs is 1 plus x over square root x squared minus 1. Okay. Now, here is, and there's a parenthesis there to match that parenthesis. Okay, so let's go a little bit further, and I'm going to focus my energy here. So square root of x squared minus 1, x squared over the square root of x squared minus 1, minus 1 over x plus the square root of x squared minus 1. And then here, add these together, common denominator would be square root of x squared minus 1 plus x over the square root of x squared minus 1. Now, what do you see? Do you see anything? I see something. I see in the end, look at this beautiful thing. X plus the square root of x squared minus 1. X plus the square root of x squared minus 1, just written in the opposite order. But that is the same, so they can cancel. That's beautiful. Oh, that's really beautiful. And actually, look, it gets even better. See there, the square root of x squared minus 1 in the second and third term now, same denominator. So we can just put them together. So what do we have? Well, we have, this is 1 half. There's the square root of x squared minus 1 there. Then plus x squared minus 1. So there's x squared minus 1 over the square root of x squared minus 1. But wait. Look at this part. Look at this part. you see it? See, it's x squared minus 1 to the 1 upstairs, if you like, x squared minus 1 to the half downstairs. So when you put these two together, you can put it as simply a square root of x squared minus 1. In other words, see, it's to the 1 upstairs to the half downstairs, and you subtract. 1 subtract a half is a half. They're the same. Oh, so if I add these together, it's like I have 2 of them times a half leaves us with the square root of x squared minus 1. Okay. Whew. Wow. Now, one of the things we're learning is functions which aren't that crazy looking, it's not the craziest looking function, have quite the expression when we try to find something that is the antiderivative. Shows you antiderivatives are hard. But now I think we're in great shape to finish the problem, because it turns out y prime is beautiful. See, watch. We're going to fly through the problem now. We're going to go 1 to 5, square root of 1 plus square root of x squared minus 1 squared. Well, square root squared, they undo each other. So 1 to 5, square root of 1 plus x squared minus 1. And you say, hey, the 1's cancel. Perfect. So 1 to 5, square root of x squared. Wait, square root of x squared, that's easy. 1 to 5 of x. Oh. So this is integral 1/2 x squared from 1 to 5, which becomes 1/2 5 squared 25 minus 1 squared 1. 25 minus 1 is 24. Divide by a half leaves us with our final answer of 12. That's the answer. 12. Wow, beautiful. Oh my goodness, it's amazing. It's a beautiful answer for a beautiful problem. Sometimes after this, you just have to sit back and enjoy it. Math is great. And sure, you have to be careful, pay attention to your algebra, but once you start seeing, things that look complicated can have really nice, beautiful answers, it just warms your soul. It warms your soul. All right, well, thank you for coming and joining me, and hope to see you again another day. Take care.